Okay, so as usual, I've got some of them highlighted. That helps keep me from straying too far. So let's see, number one. Number one. Number one, for the reaction of sodium bromide with chlorine gas to form sodium chloride and bromine, the appropriate half reactions are. Okay, so we've got sodium bromide and chlorine gas. Sodium bromide and chlorine gas produces sodium chloride and bromine. There we go. Okay, so we need to decide which one is oxidation and which one's reduction. Right. In this case, we don't actually have to split it into half reactions to balance it because we don't have any oxygens, we don't have any hydrogens to deal with. So we can actually do this one in one shot. But we do have to determine the oxidation state for each of the elements. According to the rules, single elements in their most stable state at room temperature and 1 atmosphere pressure are zero oxidation state. And oxidation state is a bookkeeping scheme for following electrons. It doesn't necessarily mean the charge. In this case, it does. Right? There's no charge on that. There's no charge on this either. It's oxidation zero. The chlorine is a 1 minus and bromine is a 1 minus because they're halogens, and sodium is an alkali metal, so it's 1 plus, and it's also 1 plus over here. So sodium is not involved at all in the redox part of this reaction. What we get is this bromine loses an electron. So there's a loss of 1 electron for every bromine. And the chlorine gains 1 electron per chlorine. Right? But we have 2 chlorines here. So we need 2 chlorines over here. All right, so that's 2 electrons. Now we have to balance the electrons. So for this one, we got 1 bromine there and 2 bromines there. So we need 2 equals 2 electrons, but we need 2 bromines here. And that gives us 2 sodiums also. So that balances the equation. Now we need to remove the spectators. Right? The sodium is a spectator on both sides. So what we need is let's see, they want it in oxidation reduction. So oxidation first. Oxidation is a loss. So we need the first one is 2 bromine ions yield a bromine here plus 2 electrons. Because it's oxidation, the electrons have to be on the product side. The reduction is the chlorine side plus 2 electrons yields 2 chloride ions. Right. So those are your 2 reactions, the 2 bromines and the chlorines. So B should be the correct answer. Okay. Righty. Number 2. Oops. Number 2. Ammonium metavanadate reacts with sulfur dioxide in acidic solution as follows. Let's see. The ratio of X to Y is, okay, What I'm looking for is, do we need to introduce water? I don't think we do. I think we can get by with this one just like we did the first one. VO3 minus, VO3 minus, plus SO2 yields VO2 plus and SO4 2 minus. So oxygen is given an oxidation state of -2. So that means we have -6 total. But the addition of the oxidation states must be -1. That means we don't need to neutralize all of those. We only need to neutralize 5 of them. So this vanadium is a +5. Let's stay with the vanadiums over here. This one's a -2, and we need a 2+. So we actually need to neutralize 4 minuses. Right? So check yourself. If this is a -2, and there's only one of them, a -2 and a +4 is a 2+. So we did it right. Okay. So now let's do the sulfurs. -2 for that oxygen times 2 is -4. It has to be neutral because there's no charge. So that means this is a +4. This one, -2 for oxygen, which is -8, but we need to keep 2 negatives out. Right? So this is a +6. Okay. Now that we know the oxidation states, we can balance. All right. So from here to here, what happened? We went from +5 to +4, which is we were reduced. We added 1 electron. Gain 1 electron per vanadium. And for this sulfur, we lost +4 to +6. We lost 2 electrons per sulfur. Okay? Now, if we just want to balance the electrons, we just need 2 vanadiums, don't we? Well, let's see, what would happen if we did 2 here and 2 here? Times 2 equals 2 electrons. That being the case, is everything else balanced? The vanadiums are balanced, the sulfurs are balanced. How about the oxygens? Well, 2 times 3 is 6, 7, 8. And this is 2, 4 is 6. So that's not balanced. Okay, maybe we are going to have to go to the half reactions. Yeah, we probably will. Okay, so let's set up our half reactions. Reduction, gain of electrons. So we need VO3 minus, and that produces VO2 plus. And just to, 1 electron was gained, plus 1 electron, to go from +5 to +4. Okay, oxidation is SO2 yields SO4 2 minus, and that was 2 electrons were released. Okay, now we need 2 sulfurs, sulfur, vanadium, that's good. So now how about the oxygens? Well, we got 3 on this side, we need 3 oxygens on this side. But that means now we need 6 hydrogens on this side. Okay. We got 4 oxygens here and 2 there, so we need 2 more oxygens on this side. That means we need 4 hydrogens. on this side. 2 times 2 is 4. Okay. Now we need to balance the electrons. Okay. We just need 2 more of these. So 2 here, 2 there, 12 there, 2 here, and 6 there. Now if the electrons are balanced, we can add it together. I'll make some more room here. All right, so let's put them in the same order they are there. VO3 minus, so we have 2 VO3 minus. And then we have SO2, SO2. And then we have 2 water and 12 hydrogens, right? The electrons canceled. And then on this side, we have vanadium first, 2 VO, 2 plus, correct? And SO4, 2 minus, plus SO4, 2 minus. And then we have 6 waters and 4 hydrogens. Now, we could go all the way to the end and balance this equation, but to answer the question, we just need the ratio of x to y. Let's see. Yeah, x to y. What's the ratio? Well, if this is x, and this is y, and this is x, and this is y, the ratio is 2 to 1. Okay? That's all we need to know to answer the question. So the answer is C. So I was wrong the first time. We really did have to do half reactions. Let's do 3 now. So if we run out of time, these are in the exact same order and the same problems that I've done in previous semesters. So you can follow along until we run out of time, and then you can switch over to the other one and just scroll down until you get to the next one in the sequence. Oh, I'm not sure if I have this document. Okay, before I finish, I'll make a note of the ones we didn't get to. Oh, wait a minute, we already, no, 3, okay. The following reaction occurs in aqueous acid solution. In the balanced equation, the coefficient of water is. Notice that there's no water in that equation, but there will be. Okay, so we have NO3 minus, correct, plus iodide yields IO3 minus plus NO2. Okay, now we have to decide which one's oxidation and which one's the reduction. Right, this oxidation number is -1. This one, -2 for oxygen, -6 total. Hold 1 out for that negative. So this one is +5. Let's see, -2 here, -6 total, -5. Right, hold 1 out for that negative, and then we only have to balance +5. This one is -2 times 2 is -4, so this one's +4. Okay. So nitrogen is going from +5 to +4. It is reduced. So the reduction step is NO3 minus to NO2. And the oxidation step is I minus to IO3 minus. Okay, 1 iodide, 1 iodide, 1 nitrogen, 1 nitrogen. We're good there. Now, let's see. Oxygens. We got 3 on this side and 2 on that side. We need another oxygen over here. Right? But now we need 2 hydrogens over here. All right. Now we got 3 oxygens here. We need 3 oxygens here. But now we need 6 hydrogens on this side. Okay. Now, for the reduction step, we went from a +5 to a +4. So we only added 1 electron. And for the oxidation step, we went from a -1 to a +5, which is how many electrons lost? 6. Lose 1 to go to 0 and lose 5 more to go to +5. So we lost 6 electrons. Okay? So now we need to balance the electrons. We just need to multiply this one times 6. There we go. Now we can add them together. So let me put them in the same order as that one. Nitrate first, 6 nitrates. And then the iodine. Here, 1 iodine. And then 3 water. And the electrons are canceled. And 12 hydrogens. Yield. Let's see. Iodate. Here we go. Iodate. Is that right? Yep. One of those. And then 6 NO2. And then we have how many waters? 6 waters. And how many hydrogens? 6 hydrogens. Okay. Okay. We're in acid solution. That means we leave it as is. Once we've balanced it, we don't have to change anything. All right, so we got 3 waters on this side and 6 on that side. These waters are gone. These are 3. Does that answer the question? Coefficient of water. Yeah. Coefficient of water is 3. So we don't have to go any further. We could if we wanted, but that's all it takes to answer the question. All right. 4. Number 4. Okay. The following reaction occurs in basic solution. Okay. Excuse me. Fluorine plus water yields oxygen plus fluoride ion. Okay. That's an oxidation state of 0. That's an oxidation state of 0. This is -2 and that's +1. And this one is -1. Excuse me. So when we go from this fluorine to that fluorine, we have to gain 1 electron for every fluorine. So that's the reduction step. We go from this fluorine to this fluoride, and we gain 1 electron for every fluorine, but there are 2 of them. So I'm going to do it that way. For the oxidation step, we went from a -2 to a 0. So we have water goes to oxygen. And in this case, we lost 2 electrons for every oxygen. But there are 2 oxygens here and there are 2 oxygens here. So that means we actually lost 4 electrons. All right. So let's see. That one's okay the way it is. This one has 2 oxygens here, 2 oxygens there, but we've got 4 hydrogens here. We need 4 hydrogens on that side. Now we need electrons. This one needs to be multiplied by 2 to balance the electrons. So there's 2 here, 4 there, 4 there. Now we can add them together. And let me check the question again. Basic solution. Sum of the coefficients. All right, so we do have to add them all together. Plus 2 water, and the electrons are canceled. That one yields 4 F minus plus an oxygen plus 4 hydrogens. Now we're going to convert it to basic. So we're going to add 4 hydroxyls here and make 4 waters. And then we're going to add 4 hydroxyls on this side. Okay? So 4 waters on that side and 2 on this side means these are gone. And now we only have 2 left on that side. So we've got 2 fluorine, 2 difluorides. We got 4 hydroxyls. We have 4 fluoride ions. We have 1 oxygen and 2 waters. So that's 2 plus 1 is 3 plus 4 is 7, 11, 12, 13. So the total of the coefficients is 13. All right. Number 7. For the redox reaction, 2Fe2 plus Cl2 yields 2Fe3 plus 2Cl minus. Which of the following are the correct half reactions? Okay. So let's see. Let's put them over here. We have 2Fe2 plus Cl2 yields 2Fe3 plus 2Cl minus. Okay. I don't think we're going to have any oxygens or hydrogens in here, so we can just say this is 0 oxidation state. That's -1. This is +3. This is +2. So we got them already. What happens here? We lost 1 electron for every iron. In this one, we gain 1 electron for every chlorine. Times 2 equals 2 electrons. And this one is times 2 equals 2 electrons. So that's good. Okay, so we need which of the following are correct half reactions? All right, so the loss is an oxidation process. The oxidation is 2Fe2 plus yields 2Fe3 plus 2 electrons. Correct? Yeah, oxidation step. But we can simplify this one further, can't we? This one is Fe2 plus yields Fe3 plus 1 electron. And the reduction is the other one. So we have chlorine plus 2 electrons yields 2 Cl minus. All right. So, where do we find this one? This one is Roman numeral 1. And this one is Roman numeral 4. Okay, so A is the answer to that one. Number 8. How many electrons are transferred in the following reaction? All right, we have 2 ClO3 minus, correct? 12 H plus, and 10 iodide, then 5 diiodide, plus a chlorine, plus 6 water. All right, how many electrons are transferred? Well, this oxygen is -2, so 3 times -2 is -6, hold 1 out. We only have to balance that minus with a +5. This iodine is 1 minus, this iodine is 0. This chlorine is 0. So if we go from this iodine here to that iodine, we have lost 1 electron per iodine. Times 10 equals 10 electrons. Now let's see if we got 10 electrons transferred the other way also. We go from this chlorine to that chlorine. This is gain 5 electrons. Went from +5 to 0. 5 electrons per chlorine times 2 chlorines, right? Equals 10 electrons. So 10 electrons were transferred in this process. That's E. $11. All right. Consider a galvanic cell based on the reaction Fe2 plus dichromate yields Fe3 plus chromium 3 plus. In acidic solution, calculate the voltage of the standard cell carrying out this reaction. All right. So let's write the reaction first. Fe2 plus dichromate 2 minus 2 plus yields Fe3 plus Cr3 plus. Okay. This is obvious here. 2 plus to 3 plus means this one lost 1 electron per iron. So that's your oxidation step. This is the reduction step from here to here. So what is this one? Well, -2 for that oxygen, -14, hold out 2, -12, that's +12, means each one is +6. So that's obvious. This one gained 3 electrons per chromium. All right, since this is a intensive property, this voltage, we just need to know which half reaction is which. Right? So the gain, this is going to be the cathode, right? The gain. This is going to be the cathode, which will be the we'll leave the reduction potential alone. We'll flip it for this one. Right? So what we need is Fe2 plus, actually Fe3 plus an electron yields Fe2 plus. Right? What's the standard potential for that one? Well, let's see. I think I'm going to have to go, rather than go to the bottom, let me just look it up in my hard copy. Maybe it would be better. Get it recorded. So we'll come back to 11. Let's go down to the reduction potential. Come on. Come on. Reduction potential. It's down here somewhere. There we go. We're getting there. Here it is. Okay, let's look for iron. Iron. Not there. Here it is. Fe3 plus electron. Yes. Fe3 plus electron. And that is 0.77 volts. Okay. And dichromate gains electrons. So we need dichromate plus electrons yields chromium 3 plus. So let me look for dichromate ions. Not on that side. Let's look over on this side. Oh, maybe it is on this side. Here it is. Here it is, right here. Right there. Dichromate to chromium 3 plus. And this reaction has hydrogens and water in it. That's 1.33 volts. So this one is 1.33 volts as a reduction. This one is an oxidation. So if we flip it, that means 1.33 minus 0.77 equals what? Let's see, 7 from 13 is 6. And 7 from 12 is 5. 0.56 volts, correct? 0.5. Let's go back up to number 8. Oh, no, not number 8. Sorry. Number 11. 0.56 volts. There it is. That's D. We didn't have to balance the whole equation. We just needed to find the half reactions that included those species. Let's see. 14. All right, 14. A strip of copper is placed in 1 molar solution of copper nitrate, and a strip of silver is placed in 1 molar silver nitrate. Okay. The 2 metal strips are connected to a voltmeter by wires, and a salt bridge connect the solutions. Following standard reduction potentials apply. Which of the following statements is false? All right, so which one's going to be the anode and which one's going to be the cathode? The copper would have to be the anode, because that's the only one we can flip and still get a positive value. Right? So copper 2 plus is the anode, and the silver 1 plus is cathode. Okay, so electrons flow in the external circuit from the copper electrode to the silver electrode. Yes, that's true. Anode to cathode. So A is true. How about B? The silver electrode increases in mass as the cell operates. Yes, we're taking silver ions out of solution as we add electrons, and we're making silver metal. So B is true. C. There is a net general movement of silver ions through the salt bridge to the copper half cell. No. Those silver ions are being drawn to the electrode and plated out here. They don't move across the salt bridge. Right? What moves in the salt bridge is cations and anions that are in the salt bridge. Right? So C is false. Oh, we don't have any wonky ones, so we found our answer. Okay. Let's see, we can get two at once there, 15 and 16. Which of the following species cannot function as an oxidizing agent? An oxidizing agent means it cannot be reduced. Right? You cannot add electrons to it. How about sulfur? Can you add electrons to that? Yeah. In fact, it prefers like that. So sulfur's good. It can be reduced. How about NO3 minus? Well, let's see. NO3 minus, the oxygen is going to be in -2. That's -6 total, -5 balance, +5. Oh, yeah. You can add electrons to that. Right? Nitrogen can go down to -3. Right? So this one's good. That one's good. How about C? We've already reduced chromium. Right? CR207, 2 minus. That's -2, -14, -12. That means +6. So yeah, we can go to +3 easily. How about D? Can we reduce iodide any further? No. That iodide has that extra electron. It's got a full octet in its valence shell. Doesn't want any more. Right. So we found our answer. 16. Which metal, aluminum or nickel, could reduce zinc to zinc metal if placed in a zinc solution? Okay. We want to reduce zinc. So is it aluminum or nickel? So aluminum and nickel must be oxidized. They must be anodes. If we're going to take zinc and make zinc metal at -0.76 volts. Yeah. So what we need is one of those to become the cathode. So if we take nickel and reverse it, that's +0.23. We still got a negative number, right? So it must be aluminum. Aluminum reversed to +1.66. Yeah, that's a positive value. So aluminum is the answer. Aluminum will do the job as acting as the cathode. All right. Oh, we got a lot here. And there's, what's the E for this cell? Oh, that's simple. Right? Let's see. These are written as, let's see, number 17. Let me write that up there. So for number 17, if we want to know the standard standard potential for this galvanic cell, since the standard potential is an intensive property, all we need to know is which one's the cathode and which one's the anode. So the bromine appears to be the anode and needs to be reversed, except that'll give us a negative number. So this cell is going to run backwards. It's going to run from chromium to bromine. Yeah. So it'd be 1.090 plus 727. So it'd be 7, 11, 8, 1.817 should be the voltage there. A. Is that right? Yeah, A. A is the answer to this one. That could fool you if you always expect the anode to be on the left, and that's by convention it should be. But in this case, it's not. It's going to run backwards, and we can tell by the standard potentials which way will it go to give you a positive value. How about this one? What's the question for this cell? There's the standard reduction potentials. Oh, okay. What's the E for this one? Well, let's see. They're both positive. So which one, if you flip manganese, you're going to get a negative number. If you flip chromium, you're going to get a small negative number against 1.506. So what number is this? 18? Yeah, 18. So we need to flip the 1.330 and leave this one 1.506 intact, and that's 671 0.176 volts. C? Yes, C is the answer. How about this one? When current is allowed to flow, which species is reduced? All right. We can't just assume that it's anode on the left and cathode on the right. What we have to do is decide which side is reduction, which one is the cathode side. And the cathode side is the one that we leave alone. All right. So the manganese, if we leave the manganese positive as a reduction and flip the chromium to minus 1.30, that'll give us a positive value. So the one that's going to be reduced is the MnO4 minus, right? C, right here. And it's simply based upon the fact that that's the only way we can get a spontaneous reaction. Let's see, that was 19. I didn't write it up there, did I? Yeah, that's all right. 19. Let's go to 20. Let's see. What is the value of Q for this cell reaction? Okay. In this case, what we have to do is create a balanced equation. And notice that these two half reactions have different numbers of electrons. So we've got to balance these equations for those electrons. Right? MnO4, right? Which one is going to be the oxidation step, the anode? The chromium one. So the oxidation step is going to be the flipped chromium, 2Cr3 plus. You know what? No, we better write the entire equation. Yeah, we better do that. Cr3 plus water plus 7 waters yields dichromate plus 14 hydrogens plus 6 electrons. And the reduction step is going to be the other one as it is. MnO4 minus plus 8 hydrogens plus 5 electrons yields Mn2 plus 4 waters. Okay. Now, this appears to be balanced as the separate equation. We need to balance the electrons. 5 here and 6 there. So we need to multiply this one by 5 and multiply this one by 6. Right. So we have 5 here and 6 here. Okay. So this one's going to be 10 Cr3 plus 35 H2O yields 5 CR2O7 minus plus what's 5 times 14? 70. 70H plus 30 electrons. Okay, this one's going to be 6 MnO4 minus plus 48 H plus 30 electrons, 6 manganese plus 24 water. Now, when we try to add these together, of course, the electrons are canceled, but we need to remember that N equals, well, maybe we don't. We only have to calculate the Q. So we don't need to know N for the Nernst equation. We just need to know what Q is. Unless, is there going to be another one? Looks like it's based on the same thing. So yeah, we better balance the whole thing. Oh, by the way, this was 20. All right, so when we add them together, we're going to have 10 CR3 plus. Only got 15 minutes left. Let's see, 10 CR plus 6 MnO4 minus plus 35 H2O plus 48 H plus 30 electrons. I'll just keep the electrons for now. And then on this side, we have 5 CR2O7 minus, and then plus 6 Mn2 plus 24 water plus 70 H plus 30 electrons. Okay, now we need to do some cancellations. Let's see, waters. Got 24 waters on this side. That means 11 on this side, right? 24 from 35 is 11. We got 48 hydrogens on this side. 48 from 70 is 22. There we go. Okay. So this one wants to know what the Q is. We have to write the K expression. Right, the equilibrium expression for this equation is CR2O7 2 minus to the 5th power, and manganese or manganese 2 plus ion to the 6th power. Then we have 22 hydrogens. Uh, 22, there we go. And then we need the reactants on this side, chromium 3 plus to the 10th power, MnO4 to the 6th power. Water doesn't count because it's a pure liquid. So that's it. Now we just plug in the numbers. So what's the chromate concentration? Chromate is 0.3. 0.3 to the 5th power. Mn2, 0.2 to the 6th power. Hydrogen ions, 0.01 for both of them. Right? There's only one place for it, so it has to be 0.01 to the 22nd power. Chromium 3 plus, 0.4 to the 10th power. And MnO4. That's a minus, right? Ah, here it is. MnO4. 0.1 to the 6th power. There we go. So that should calculate our Q, if I did everything right. Let's see. 0.3, enter. 5 to the power. 0.2, enter. 6 to the power times 0.01, enter. 22 to the power times that. And 0.4, enter to the 10 power, divide, and then 0.1, enter to the 6 power, divide. I got 1.48 times 10 to the minus 41. N to the minus 41. Or round it off. Yeah, I better round it off because we don't have 3 significant figures. So that should be, is that what they got? Yeah, B. That was a lot of work for one little answer. Let's see, they're going to want 21 also. They want to know what is the coefficient of H plus. Coefficient of H plus. Oh, 22. 22, D. So 21 is D right here. $22 the same? Looks like it. What's the cell potential at 25 degrees as read on the digital voltmeter? Okay, now we're going to take 22 and we're going to use Nernst equation. So E equals E0 minus 0.0591 over N times log of Q. So how many moles of electrons were transferred? 30. 30 moles of electrons. So what's E0? We have to calculate E0. So E0, let me be sure we're working in the right one. Same concentrations, 4301, 1201. Looks like the drawing was switched. No, it wasn't. Okay. All right, E0 is 1.506, 1.330. 1.506, 1.330. This one has to be subtracted. All right, so that's 671, 0.176 minus 0.0591 over 30. And then the log of 1.48 times 10 to the minus 41. All right. Let's do that log first. Since I've already got it in my calculator, I'll do the log and then divide by 30 and multiply by 0.0591 and then change the sign because I'm going to subtract a negative and add 0.176. So I get E equals 0.256 volts. Thereabouts. E, right? Yeah, E. 0.26 volts. There you go. Let's see, we're going to need that mess anymore. I don't think so. Okay. Oh, I got 10 more minutes. Let me see how fast I can move. I think that's right. Fast runs to 5, doesn't it? Yeah, well, 5:05. All right, number 30. The following reaction has a voltage of 0.92 volts. So this one has okay. I think they're saying this. No, they're actually saying that the actual voltage of that cell is 0.92 volts. 0.92 volts. So this is a trick question. If the conditions are standard, 1 molar concentration for mercury and hydrogen ions and 1 atmosphere pressure for hydrogen, that means this half reaction is being compared to the standard hydrogen electrode. So if we measure plus 0.92 volts, that is E0 for the half reaction of mercury. So that is also E0. D is the answer. We skipped a bunch of them, didn't we? There's a lot of repetition. Here we go. '44. An excess of finely divided iron is stirred up in a solution that contains copper 2+ ion, and the system is allowed to come to equilibrium. The solid materials are then filtered off, and the electrodes of solid copper and solid iron are inserted into the remaining solution. Hear that beeping again. I don't think it's a bomb, so I'm going to ignore it. Allowed to come to equilibrium, and then the solids are filtered off and the electrodes are placed back in the solutions. What potential develops between these two electrodes at 25 degrees? That's another trick question. If the solutions are at equilibrium, there's no voltage. The galvanic cell is dead. So you can put new electrodes in there, it doesn't matter. The voltage is still 0. Equilibrium is the key word to that whole question. All right, 49. You make a cell with an aluminum electrode in a solution of aluminum nitrate and a zinc electrode in zinc nitrate. If you could increase the concentration of aluminum, which of the following is true about the cell potential? All right, so we got aluminum nitrate and zinc. So we got aluminum. Zinc is more active, so it wants to be reduced. Zinc is going to be on this side. Zinc nitrate is going to be in this one. And it's going to go over here to aluminum with our salt bridge. Aluminum. If you could increase the concentration of aluminum, which of the following would be true about the cell potential? Well, maybe not. Let's look at the potentials. Aluminum 3+ and zinc 2+, reduction potentials. We better look at the real values here. All right. So let's see. Scroll down, scroll down. Looking for aluminum or zinc. Okay, not on that side. Look on this side. There's zinc, and there's aluminum. Zinc is the cathode. And aluminum is the anode. Right? Because zinc is above aluminum in that process, we would have to change the value we'd have to change the sign on 1.66 positive now, minus 0.76 to give us a positive value. Okay, so aluminum has to be on this side. And now we go back to the question, which was 49. Right? What would happen if we increase the concentration of aluminum? Increase the concentration of aluminum. Well, in this case, we're trying to go aluminum to aluminum 3+ plus electrons. So if we increase this concentration, it would drive it back to aluminum and would not allow oxidation. It would decrease the effectiveness of the oxidation, which would decrease the voltage. So the cell potential would decrease. All right, I got just a few more minutes. Let's see if we can get 56 out. How many moles of electrons are produced from a current of 14.4 amps in 3.2 hours? 3.2 hours. Amps are in coulombs per second. So we need to find out how many seconds that is. How many seconds in an hour? We've done this one before. 3,600. 60 times 60. Right? So that gives us seconds. And then we have current of 14.4 amps. 14.4, and an amp is a coulomb per second. So that cancels seconds, so leaves us with coulombs. And now we need to convert coulombs to moles of electrons. So that's 90. What is that value? Faraday's constant. Let's see. Where is it? I don't have it memorized, so it needs to be in here. Just got to find it. 96,485. 96,485 coulombs per mole of electrons. Okay, does that answer the question? How many moles? Yeah. Okay, so 3.2 times 3,600 times 14.4 divided by 96,485. So that's, let's see, three significant figures. 1.72 moles of electrons. B is the answer. Okay. Well, I'm out of time. So let me see. The ones we missed are 64, 72, 75. That's it. We just missed 3. Okay, that's enough for one day.